right, why don't we begin? So today's speaker is Mac Jones Jr., who I think many people know, but he is currently a National Research Council postdoc at the Naval Research Laboratory, and Mac received his BS in meteorology from Millersville University in 2010, and when he was undergraduate, he actually spent a couple summers here at HAO as a SOAR's protege, and then he came to Boulder to go to the University of Colorado to do his master's and PhD, which he received in 2015. And his research interest is in developing an understanding of how synoptic scale waves of lower atmospheric origin impact the dynamics, thermodynamics, and chemistry of the ionosphere-thermosphere system. And he primarily has used the NCAR TIE GCMs and Time-CDM for this work. So, Mac, please go ahead.
Can everybody hear me? All right. So it was funny. I was walking up here, and I think I made a joke to Dan Marsh that the first time I was in this room was 10 years ago. I think right around this time, doing the writing workshop for SOARs. And it's funny because I don't think any presentation I would have given that year would have been up here. So I really owe a lot to SOARs. And it's just great how to see everything can come full circle. So I'm going to break my talk down into 3 parts. This is all work that I've done over the last 2 years as part of my postdoc. So some of the results, especially the things that I will show early on, will be from previous versions of models. And so I've tried to point out. And so I'll start with some introduction and background, just to give everybody an idea of sort of my interests and why we're so interested in interannual variability in the thermosphere and ionosphere, and connecting that down to what happens in the middle atmosphere, the stratosphere, and the mesosphere. And then I'll talk about a specific feature, climatological feature that we see in the thermosphere, the semi-annual oscillation, and then how this work has evolved to nudging the Time-GCM here at NCAR using a newer reanalysis data assimilation product that the Navy has, which is HA NAVGEM, or the High Altitude Navy Global Environmental Model.
Matt, you're getting some green. I think maybe turn off the podium lights. I don't know if that's it is off.
Okay.
Maybe just move it down.
Better?
Is that better?
No? Yes?
Oh, gosh. Anybody know how to operate this thing?
I think we can.
It's better. I think it's a little better now.
Is it better now?
Yeah, it is.
Okay. All right. So just to start, just a brief overview of just general atmospheric structure. So where's my? Wait for it. I have a pointer.
Sorry, I threw you off your game.
Hey, there we go. All right. So is that working now? It's still working?
Okay. You can move it back up.
Good?
Yeah, that's good.
Okay. So just a general overview of the atmosphere here, just a nice picture. We're going to spend most of our time up here in the mesosphere, thermosphere, and ionosphere. And so just a general look into the thermosphere. It's driven by the absorption of solar radiation and the extreme ultraviolet soft X-ray by O2, N2, and atomic oxygen. And the important part about this specifically for this talk is the structure in those molecules and atoms with altitude. Because the thermosphere is in a diffusively separated part of Earth's atmosphere, species with lighter molecular mass fall off less rapidly with altitude. And so things that are minor constituents, like oxygen, for example, down in the lower thermosphere become the dominant chemical constituent at higher altitudes, and thus control thermospheric density. And so embedded within Earth's thermosphere is the ionosphere, which is typically broken out into the D, E, and F region, and is characterized by this sort of characteristic electron density profile. And specifically below sort of our peak density and electron density in the F region, typically the first order consider that the ionosphere is in photochemical equilibrium. And so in that sense, O represents sort of our source. Photoionization of O is the dominant driver of the electron density here in the ionosphere. And then N2 as well as O2 act as sort of the dominant loss mechanisms through charge exchange and dissociative recombination. And so you can see that the electron density is proportional to changes in the O to N2 ratio, which you'll see me talk a lot about today. But the other part of this is, you know, the thermosphere and ionosphere is the part of the atmosphere where we transition from our atmosphere into space. And so we want to be able to forecast better for obvious reasons, satellite debris, satellite navigation, and all these things. And so over the last sort of 25 years or so, there's been this shift in the paradigm of this singularly solar-forced thermosphere to this idea of waves with lower atmospheric origin forcing and driving what we nominally call space weather. And so this is a schematic here that was from the decadal survey representing sort of the lower atmospheric forcing of gravity waves and tides, which are just two of the types of waves that you would get that can contribute and drive some of the variability in the thermosphere and ionosphere, as well as pointing out sort of this mesopause region where these waves typically break and drive what we call turbulence, mixing, and what's typically parameterized in general circulation models is eddy diffusion. And so just briefly, gravity waves are small-scale waves that result from just the general disruption of Earth's atmosphere stratification. It can be driven by thunderstorms, frontal systems, flow over topography, even tsunamis and earthquakes. Tides are larger scale oscillations, global scale oscillations that have periods that are subharmonics of a solar day. And they also can be generated just from the daily cyclical absorption of ozone and water vapor in the troposphere and stratosphere, as well as latent heat release associated with deep tropical convection. So what ends up happening, these waves start propagating vertically in altitude, and depending upon their phase speed and the mean background winds, they can either be filtered out, or they can actually get up into the mesopause region or the MLT region, where they dissipate, break, drive mixing, which is important for mixing up the thermospheric constituents that I previously talked about, as well as dissipate, here, let me highlight these, dissipate and drive the mean flow. And so we're going to spend a lot of time talking about today, specifically, how this region of Earth's atmosphere contributes a lot to what we see up here, and specifically as we transition from a well-mixed atmosphere into a diffusively separated atmosphere. So just some brief background on sort of the intra-annual part of the talk, the intra-annual variability part of the talk. So I'm going to talk mainly about the annual and semi-annual oscillations in Earth's thermosphere and ionosphere. So they were first discovered back in the 1960s from satellite measurements. And this is in globally average density and electron content, and electron density, things of those nature. And so you can see here just down, I have a plot of interannual variability and mass density of 400 kilometers from the global average mass density model developed by John Emmert and Mike Piccone at NRL from orbit-derived density data. And so what you see is variations in global average density relative to their global annual average at 400 kilometers. And you notice there's this nice sort of semi-annual variability with 2 peaks at the equinoxes and 2 minima at the solstice. And so embedded within that is also an annual oscillation that you have a peak in June, or excuse me, a minima in June solstice and a maxima in sort of the December, January time frame. And so the interesting part of this is we've known about these oscillations for a long time, but models still struggle to do this. And so for all the Wacom people, I tried to make sure I put circa 2014 as the older version of Wacom. This is when I got there. This is what I was able to work with. So this is, so in blue you have the TIE GCM, and then you have an SD Wacom run from Fabrizio Sassi at NRL. And what you see is basically the same thing. So we're looking at the percent change relative to the global annual average of mass density of 400 kilometers. And so what you know is sort of the standard version of TIE GCM shows no semi-annual variation, but it does have some Earth-Sun distance effect in the annual variation. But it also, the Wacom results show SAO that's 180 degrees out of phase from what you would expect from observations. And so it wasn't until recently, in 2009, Chen et al. Suggested that sort of this idea of eddy diffusion, wave breaking, has this semi-annual variation associated with it. And that acts to mix up constituents at the base of the thermosphere, which then gets permeated to higher altitudes. And so they were able to sort of replicate this semi-annual oscillation in density.
I'd say that the standard model has some semi-annual.
Yes.
And you can see it in there if you look. And it has some annual, mostly because of the sonic distance. And that's commensurate with what Tim Fleurel found
With the thermospheric spoon.
16 years ago. But it's just not strong.
Yeah, and so, yeah, that's a fair point.
And that's why we jacked up the lower condition in order to get enough variability in there to reduce damage.
Absolutely. And so the point of this is really to say, okay, so we've made incremental steps. We think it's lower atmospheric forcing that may be driving these circulations. But when you change a parameter like KZZ or eddy diffusion, that affects all constituents. And it also affects dissipation of momentum as well. And so it can have some unintended consequences. And so that served as sort of motivation to what we're currently doing. And so this is some motivation offered by some work done by Dave Siskin, where they were looking at putting in sort of the no-gaps alpha lower boundary into TIE-GCM and evaluating its effects in the ionosphere. And so what they did was they included realistic tidal forcing and nudging sort of just above the model lower boundary in the TIE-GCM, which is around 97 kilometers, to see how it modifies the vertical transport in the neutral constituents and thus maps itself to the ionosphere. So just really quickly, so they had 4 different runs that they did. One, which is the standard NCAR run that uses a constant eddy diffusion value as a function of day of year or month. And so at the lower boundary there is just the migrating tide, so just the diurnal and semi-diurnal migrating tide. Then they performed a second run where they used the Chen et al. KZZ variation. And then they performed 2 extra runs, one in which they put the no-gaps forcing, which is a data assimilation product that is run at NRL with the sort of this constant eddy diffusion value. So they wanted to do that to put in more forcing from non-migrating tidal components, as well as more accurate specification of the migrating tides. And then they performed a run where they used this no-gaps forcing and lowered the eddy diffusion value by a factor of 5. And so this is the results is what you see here on the left. And so you have monthly mean electron density at the peak of the F2 in the F2 region, where the black dotted line or asterisk line is from cosmic. And so what you'll notice is sort of run one shows something very similar to what I just showed for the ionosphere, or for the thermosphere, but as you can see, those two are very clearly related, as we talked about. And then we have the Chen et al. Run, which looks pretty good. But then when you start to include this dynamical forcing from gravity waves and tides, you see that the ionosphere is lower by a factor of about 2 or 3 in some places. And then when he lowered the eddy diffusion value, it started to go back up. So thus, once again, showing that there is some relation between how strong you have this eddy diffusion relative to the actual physical mixing you put in at the resolve scale from tides and other waves. And so what they concluded was you either need to reduce values of eddy diffusion when including realistic dynamical forcing, or reconsider sort of the O lower boundary condition in TIE-GCM, which assumes you're at the peak, and that peak does not vary with day of year. And so this is sort of one motivation for kind of the work that we're doing as well. So over intraannual and interannual, even though I won't be talking about interannual, sort of the mechanisms that connect the middle, so where these waves are being forced, the middle atmosphere and the lower atmosphere to the upper atmosphere sort of remain poorly understood on interannual and annual and intraannual timescales. And so what you have here is a plot of normalized eddy diffusion. So in this sense, in most GCMs, it's put in as sort of this time scale or a time constant, and it gets multiplied by the scale height squared to give you your typical diffusion units that you see. But what you notice is you have the Chen et al. Specification here, and this is globally average at the TIE-GCM lower boundary, so right at the mesopause, 97 kilometers or so, as a function of day of year. And you'll notice these, the big semi-annual variation that was put in. Then you kind of have the sister model of the TIE-GCM, the Time-GCM, here at NCAR, whose lower boundary is down in the stratosphere, about 30 kilometers. And so it doesn't have this boundary right in the mesopause region where there's a lot of mixing going on. And you'll notice its value is much smaller. It has some semi-annual variation to it, but is much weaker, especially at certain points in the year. And then you have this recent result from Salinas et al. In 2016, where they resolved and calculated eddy diffusion using a 1D continuity equation from SABRE CO2 measurements. And so you can see the Time-GCM here actually does pretty well. It's not terrible. It's definitely not as strong. You don't need the variation that you see there to sort of get the right chemical composition up at higher altitudes. And so that's one motivating, that's one of our dominant motivating factors. The other is sort of this idea of the difficulty of GCMs properly accounting for variations in atomic oxygen near the mesopause. And so this is a Time-GCM run showing atomic oxygen at 94 kilometers, a function of day of year and latitude. And you can see that OSIRIS and SABRE both show summer maxima in the O at high latitudes, but the Time-GCM is 180 degrees out of phase. So we have these two things going on where we're trying to predict what's going on in the upper thermosphere and ionosphere, but what ends up happening is down where we start to transition from a fully mixed atmosphere to a diffusively separated atmosphere, we're not getting those two things right. And so what's wrong down below will always be propagated up through molecular diffusion. All right, so this is just another thing sort of hammering home this idea of composition being an important part of this whole picture of trying to do a better job of simulating these interannual variations in the GCMs. And so what we have here is a function of year. So we have multi-year run. I think this is a 5 or 6 year run of the TIE-GCM using the Chen et al. Specification of KZZ at the TIE-GCM lower boundary versus GUVI column O to N2 ratio. And what you can see is down here, as we start to get into this, the summer solstice time, that the TIE-GCM sort of over-predicts the amplitude of the annual oscillation when you include this KZZ specification. And so that either implies sort of a deficit of O, so there's not enough O in the model, or an abundance of molecular nitrogen. Especially, and so this is, I should also point out, this is at mid-latitudes as well. But the question is, well, what consequences does that really have on the ionosphere? We've obviously shown that O to N2 ratio and electron density are proportional to one another. So what ends up happening when you see this? So this is for June solstice for a couple of different simulations. So this is from the TIE-GCM with the runs that I previously talked about. This is from the Time-GCM. This is from the TIE-GCM where Doug and others have specified the composition at the TIE-GCM lower boundary, allowing that to vary with day of year as opposed to holding that fixed, and then comparing it to the IRI climate, empirical model for, we have electron density profiles here at 15 local time here in solid, the solid lines, and 3 local time here in the dash. And so what you can see is when you include, or when you have these low values of O, you lose this F2 peak when the KZZ values are really ramped up. And so it's basically to say that we've lost this F2 peak, or our peak electron density in the ionosphere, that you sort of recover when you have these KZZ values that are much less, or in the case of the blue line, where you actually have specified some varying composition at the model lower boundary. And so the real take home in this slide is sort of the inclusion of dynamical and chemical processes near the O peak, and also mesospheric variations in atomic oxygen are very important for recovering the F2 peak, but moreover for the whole ionosphere. Yes, Dan? Yeah, the E region's not good in general. in a lot of models, which is a known problem. There have been things I know have been done ramping up soft X-rays to try to make the E region better, but that's a problem Stan and I have talked about before as well.
It's a long span.
Mm-hmm.
Probably has multiple R-values.
Mm-hmm.
I mean, I've been saying, I solved the problem 17 years ago
Mm-hmm.
with the soft X-rays, and they took them away. So, but I think part of it is the solar specification.
Mm-hmm.
I think there's some other things going on that aren't relevant
Yeah. Mm-hmm.
Is this the 5 degree or the 2.5?
So I believe all of their runs were with the 5 degree. So the Time-GCM runs that's stuff that I perform is all 2.5 degree. So all their stuff is with the single resolution.
The reason I'm asking is because in principle and in experience, the choices of what to use in KZZ,
Yeah.
what to formulate it, are dependent on the resolution
Yes.
of the model, because KZZ is sort of whatever's left over after you finish resolving what you can resolve.
Mm-hmm. Yes, completely agree. All right, so now I think I've sort of gone over all that. So our real research objective here is to try to uncover sort of this link between mesospheric composition and the F region ionosphere. And so with that, we have two main science questions that I've worked on now for over 2 years, it seems, or just about 2 years, which is, what are the key mesospheric and lower thermospheric processes that describe the interannual variability in the coupled sort of ionosphere-thermosphere system? And then sort of what extent does mesospheric composition play in determining sort of the intra and interannual variability of the F region ionosphere and sort of its mean state? And so that's been sort of the overarching goals. And so now I'm going to move to the sort of the second part of the talk, which is focused just in looking at this semi-annual oscillation in the thermosphere and ionosphere. And so this is some work I've performed over the last year. We wrote a GRL paper on it, so if anybody's interested, I can disseminate that afterwards. But sort of the idea here is to analyze the lower and middle atmospheric forcing in composition, temperature, gravity, waves, tides, all these different influences on the SAO and the global average thermospheric mass density, as well as total electron content, or in the ionosphere. And so the way we went about this is we performed a number of different Time-GCM simulations and TIE-GCM simulations. So they were performed at the double resolution, so answering that question there, for constant solar medium conditions. So we have a constant F10.7 that's right around 110 solar flux units. And then we also had geomagnetically quiet conditions as well, keeping that low. And so you'll hear me talk and refer to the Time-GCM standard, which is we specify the tides at the model lower boundary from GSWM 2009, both migrating and non-migrating tides. The gravity wave parameterization in Time-GCM is a modified Lindzen scheme, and it has sort of this seasonally varying component, which I already showed you. Then we performed a run where we turned off this gravity wave parameterization, but still allowed the tides to propagate through in the model and specified at the lower boundary. We also have a run where we turned off the lower atmospheric forcing from GSWM, as well as the gravity wave parameterizations. In a way, it's not completely turning off the tides because you still have the stratosphere and the ozone forcing of the migrating tides. And then we also performed a TIE-GCM simulations where we used tidal lower boundary conditions from the climatological tidal model of the thermosphere and background winds and temperatures from Windy, Hardy, and Sabre. And then the gravity waves in TIE-GCM, there is no gravity wave parameterization in TIE-GCM, but we use the empirical Chen et al. Seasonally varying. And so we compare all these things to try to understand what's driving the semi-annual variation, since it's been known for about 50 years now, and I don't think it's still really clear what drives this phenomenon in the upper thermosphere. And so what you have here, it's a very busy plot, and so I'll try to explain it. So a function of day of year, you have on the left-hand side interannual variations in mass density at 400 kilometers. So this is relative to the global annual average from the Time-GCM standard in black, without gravity waves in orange, without gravity waves or lower boundary tides in purple, with the TIE-GCM with the Chen et al. Specification, and observed climatology, which is from the global average mass density model. And then the same thing here for the total electron content. And so the long and the short of it is the Time-GCM, just out of the box, you run it, you don't do anything with it, seems to produce a semi-annual variation from first principles, which was kind of astounding to us. And we didn't expect to see that. But even more interesting is that when you turn off the gravity waves, it's still there. And so it appears as if it's not gravity waves driving this thing. But then when you turn off the gravity waves and tides, the oscillation in its amplitude amplifies by a factor of 2. And so we juxtapose this then with that KZZ plot that I've already showed you, that you see when the gravity waves are turned off, it's flat, you still get this semi-annual oscillation. And that these KZZ values compare well with observations. And so just to kind of walk through it, you know, this compares well with sort of the observationally derived KZZ values that we have to date. And that when the gravity waves are turned off, KZZ is seasonally invariant, but there's still this SAO and globally average mass density. And finally, when everything is turned off, both the lower atmospheric forcing from the troposphere, specifically of tides, and gravity waves are off, there seems to be this SAO that grows in amplitude. But it seems to be sort of this resolved scale internal phenomenon that's internal to the mesosphere, thermosphere, and ionosphere system. And so just to kind of sort of hammer home this point, so what you see is, I'm sorry. Mm-hmm. How precise are the CO2 measurements?
The climatology in that graph, the upper left.
Mm-hmm. You talking about the observed climate, the red line?
Yes. How precise is that?
I can't say I know off the top of my head how precise.
These crosses, I mean, don't tell you much, but what one would like to see is, in observing that over several years, what variations are.
Mm-hmm. You talking about in the sort of in the observed climatology?
Yeah, this from Emirates.
Yeah, this is from Emirates.
It's derived from decades of tracking thousands of orbiting objects.
So from 1960, uses a repository from 1960 to 2014.
So there's a solar cycle variability in there that has to be accounted for. But in terms of this seasonal climatology, you are looking at a highly averaged result that is probably quite precise with regard to its amplitude. Because there's so many observations that go into it. There are, of course, the possibilities of systematic offsets having to do with coefficients of drag and the molecular that figure into that. But the magnitude and morphology of the annual, semi-annual variation in density at high altitude is exceedingly well known. Just from all of that tracking data.
Yeah.
In fact, that's the great thing that Emirates has done, is he's taken this massive amount of data and reduced it to an understandable form.
Yeah,
Captured it in an empirical model.
one would still sort of like to see a graph how over 5 years what the variation would be.
And I can,
Oh, yeah.
and I can show you that, and all that's in his paper. Now I can't say I can quote those numbers off the top of my head.
50-year time sequence, daily average.
Yeah.
It's all daily average also. It's not a high resolution data set.
No, it's a globally average mass density.
But from that taking the pulse from the thermosphere point of view, it's an exceptionally good data set.
All right.
Thank you.
And so just to relate this point, so this is the SAO amplitude as a function of altitude, and phase as a function of altitude in just atomic oxygen in the Time-GCM from all these different runs. And this is also compared to the MSIS product at NRL. And so what's interesting about it is specifically this phase. Oops, went the wrong way. So if you notice in the mesopause region, so this goes down to 80 kilometers and goes the whole way up to about 410 or so, that this O variation is 180 degrees out of phase from what we see in the upper atmosphere. So it has solstical maxima and equinoctial minima. But very quickly, over a 20 to 30 kilometer region, it transitions to being in phase. And we know, as I talked about earlier, O is the dominant species in the upper thermosphere, which is mainly what's driving the mass density at those altitudes. And you can see from about 100 to 110 kilometers upward, it's relatively constant.
So you may be about to tell us this, but if the Time-GCM mesospheric O is so out of phase, how on earth does it get a reasonable answer?
Well, so there's part of this. So the global average, too, is cosine weighted. So what goes on at high latitudes is not playing so much into this. It's mainly what's happening at low and middle latitudes. Now, the Time-GCM, I'm going to point out, too, after I talk about this, it still has issues. It's not perfect. And I'll show you some of those issues, which is why we kind of want to nudge the model. But you see, the point of this is to show that it matches well with sort of our empirical understanding with MSIS, but it's also very constant in altitude, meaning that whatever's going on in this sort of 30-kilometer regime is really what's driving this SAO, at least to our knowledge as of today. So in order to try to diagnose this a little bit further, and this is just to kind of restate this point, that so without gravity waves and tides in the Time-GCM, it seems to be this resolved scale vertical transport of O that seems to be driving the SAO. And so the way that we want to do this is kind of break and look at the averaged O continuity equation. But what I'm showing you here is we start with sort of just the zonally and diurnally averaged O equation as a function. And so that's production and loss of O, vertical diffusive flux, so the flux in O due to molecular diffusion and eddy diffusion. And then these two other dynamical transport mechanisms, one of which are the flux divergence due to what is termed the advective winds, or just the mean meridional circulation in the thermosphere and MLT region. And also sort of this idea of sort of a net tidal flux, or if you were to break all your dependent variables into a mean and a perturbation quantity, the residual part of that from the full field and the mean field would give you sort of the wave quantity. And do these wave fluxes in atomic oxygen drive what we see at higher altitudes? And so what we do is we just go ahead and globally average that. So we integrate over latitude and we come up with these terms that we're interested in looking at in the O continuity equation. So once again, production and loss, our diffusive flux, both eddy and molecular diffusion, our advective flux. And so the key thing is here, meridional transport has gone away. So we're looking at pure vertical transport, sort of a 1D idea. And then our net tidal transport. All right, so what you have here is a sort of this plot showing interannual variations in O, as well as sort of the global mean processes affecting O. And so in the top you have the Time-GCM standard, so that's with the gravity waves, with the tides, and then you have without the gravity waves and without the tides below it. In the two left-hand panels, these are variations in O relative to their global annual average from the two simulations. This advective flux divergence term and this net tidal flux divergence term. And so I'm not showing the other two terms, the diffusive flux as well as the chemical flux. The chemical flux is 180 degrees out of phase, and so is acting to damp whatever is being caused here by the dynamics. And the diffusive fluxes will, especially above sort of this dashed line here representing the lower boundary of the TIE-GCM, will just go ahead and do go ahead and follow sort of what O is telling you down here. So as we go up, the diffusive flux in O will look very similar to what the additive effective of these two is. And so the point is here, you can see now this phase shift. Oops, I keep hitting the wrong button. So this phase shift between it being out of phase to being in phase between 80 and 120 kilometers in the MLT region, which is consistent with what we had shown previously. But what also is interesting here is the advective fluxes seem to be in phase. So this, the average vertical transport of O seems to be in phase and sort of correlates with this phase shift as you go up in altitude. And so it might just be this idea of vertical mixing, sort of internal vertical mixing averaged over the globe that's driving the thermosphere and ionosphere SAO. But also the advective or the net tidal fluxes can also contribute to this as well. And now these kind of look funny, especially here, but when you have no gravity waves or no tides, this is 180 degrees different than this, because even though this is blue and this represents loss, there's less loss at equinox than at the solstices when you don't include gravity waves and tides, whereas when you include the tropospheric components of the tides, mainly the migrating diurnal tide, this flips sign. And it's 180 degrees out of phase with what we see here. So the point is really what we discovered, it was not only is this an internally forced sort of phenomenon, but that the lower atmospheric part of this actually acts to reduce the internally forced stratosphere-mesosphere part of it, meaning that tidal and gravity wave dissipation actually act to damp the oscillation from its sort of nominal value that we would see if we didn't force any waves from the troposphere.
And you have good reasons to believe that this averaging over latitude is a meaningful effort.
Yes, I mean, it really is to compare with our that observational data set, this sort of robust observational data set to be able to do these things. But in order to, so I admit, and this is not complete. Like I need to do more to understand what's driving that. And I think to do that, I have to get more into the latitudinal versus altitudinal, sort of that sort of meridional piece of this to really understand where this is coming from internally.
Because this is 20 years back, all the way back to the so-called tropospheric spin.
Exactly. It's
And incidentally, and Mary Angel have reported similar experiments in C50, where they get a similar result. The tides actually suppress the seasonal variation.
and from just the tidal background, it makes sense. The dominant tide in the mesopause region is the migrating diurnal tide. It maximizes around the equinoxes and minimizes around the solstices, right? It's going to dissipate more at the equinoxes, thus more mixing, thus more pulling down O out of the thermosphere, damping the oscillation. So, yeah.
About 2000?
Yeah, I wanted mid-1990s. Yeah. So it's the other sort of big hypothesis.
Wrote a paper saying that the general circulation of the thermosphere is such that at the equinoxes, because there's two-cell circulation, that it's less effective of stirring things up as the big circulation cells you get during the solstices. And he called this the thermospheric spoon, and it appeared to explain some, if not all, of the seasonal variations you see in composition of those.
Yeah, so it's kind of going back to this old idea that it's this sort of just the natural circulation in the thermosphere that drives this thing, or the mesosphere. But it's funny because it's been this long-standing problem that you would think in a global average sense that general circulation models would be able to resolve, and we haven't been.
You know why it's not reproducing TIE-GCM then?
My thought is because it's happening, the important physics lies right at where the TIE-GCM lower boundary is. And because you have this boundary set at 97 kilometers approximately with constant composition, that you're not allowing the two things to talk. You're not allowing the dynamics and the chemistry to talk with one another. Like you have this lower boundary that says, okay.
It's not constant. Composition isn't constant.
But if you look at the mixing ratios, they're set to a invariant value with latitude.
No, they change. Latitude.
So there's no latitudinal variability in that. Now they will change with day of year due to the dynamics, but the values themselves remain fixed.
For N2 and O2, but not for O. O is controlled by eddy diffusion and the transport and everything else. So O will vary on the lower boundary.
But it's still assumed to be at the peak, and that doesn't vary throughout the year.
The assumption is that O reaches its
Peak,
at
and that doesn't vary.
the solver depends on that. That's maybe.
And so that's one of the things that I have to. Time-GCM doesn't have this boundary, so it's just chugging along, doing what it's doing. And at least when I got to NRL in 2015, the Wacom X wasn't showing this, and they had an idea of what was going on in Wacom X that wasn't showing this. But after talking with some folks here today, Wacom X may be headed more in the right direction. And so the question is, what's driving this? And it's still something that I need to look into. So I'm still working on this stuff. I'm looking more in this region, and specifically sort of this meridional transport idea. So I showed some of the stuff that I just talked about at AGU, and I got a chance to talk to people with some NCAR people here about the Time-GCM and some of the things that were in Time-GCM that I may not have been privy to before doing this work. One of which is sort of this artificial momentum SAO that's put into the model to better resolve the stratosphere and mesosphere semiannual oscillation. And the way this is done is it's put in through gravity wave drag. And so I was asked, well, does that cause this? And the answer to that is no, because when you turn off the gravity wave parameterization, it shuts off everything, basically in that routine. And so no, that's not what's driving it. But then the other question was, well, what about Rayleigh friction? So what I'm showing you here is Rayleigh friction, because the model doesn't blow up when we turn off the gravity wave, so there's a linear damping term that allows it to do that. And so in the standard sort of TIE GCM, or excuse me, time GCM, this is what Rayleigh friction looks like. So it has this kind of semi-annual variability associated with it. And so what I did was I said, okay, just give me an average value at this altitude and make it constant. And so the point is it doesn't appear, so this is mass density, interannual variations again, in mass density of 400 kilometers. It doesn't appear that that's what's causing the SAO. The SAO is still there regardless if we make all these things constant and everything else. So something about this model was doing it. But it's not without its flaws. So even though it does this, there are some issues. One, so this is, I've been showing you relative differences between global annual average in density and TEC and all these things. But I haven't shown you the raw density. What does that look like? So this is this global average mass density of 400 kilometers. The dashed dot line is MSIS, and the solid line is time GCM, the standard run, and the dashed line is without the gravity waves. And so, I mean, very clearly, it's too low, and by a factor of 2, which is an issue, which may be part of the reason why it doesn't do the annual oscillation very well. So the annual oscillation is actually a factor of 2 too low in the time GCM. And so that may be related to this idea of O composition in the mesosphere, in the MLT and the mesopause region. So what you see here is a function of day of year. At 80 kilometers, which is down here, and 90 kilometers is the O density from the time GCM standard in the solid line, and the Sabre-Osiris empirical model, which is derived by was created by Doug Drob. It's basically taking the MSIS fitting and applying it to Sabre and Osiris data. And so the point is, at 80 kilometers, this is the time GCM is too high by a factor of 2, and then over a 10-kilometer range, now it's a factor of 2 too low. And so as we've talked about this whole time, this connection between what happens down in your mesopause and what happens up in your upper thermosphere are much connected. So this is an issue, and it's an issue mainly for the annual oscillation. So we're trying to figure that out, and that kind of motivates sort of the idea of nudging the model and trying to push it into the right direction. And the second part of this is there's also solar cycle variability that's associated with these different oscillations. So what you see here is this observed climatology, or this global average mass density model, again here. And this is the time GCM run at 3 different solar flux conditions. So blue is at low solar activity, green is at medium solar activity, and red is at high solar activity. And so you can see in the orbit-derived density that there's a semi-annual oscillation that increases with solar cycle. The time GCM doesn't do that either. And I don't think anybody understands quite why that is yet either. So we know that the time GCM has these issues, right? And so our next step is sort of, okay, the overall density is not great. The relative amplitude and the oscillations that it creates are pretty good. But the overall density, the composition is not very good. So can we use nudging or data assimilation in our model to tell us what the deficient physics is? And if so, does that help us point to what's driving these oscillations? And so the way we're doing that is nudging the time GCM using the High Altitude Navy and Global Environmental Model, or NAVGEM. And so just some quick background. I'm not a NAVGEM expert. This is for the people that people do this in Monterey, as well as John McCormick at NRL. And so just really quickly, sort of give you an idea of what the NAVGEM sort of system looks like in the data assimilation component. There's a couple of key things. It assimilates 300 million observations every 6 hours, and specifically the measurements highlighted here in yellow, Sabre temperatures, MLS temperatures, MLS ozone and water vapor, as well as the special sensor microwave imager and sounder aboard the DMSP satellites. So it assimilates radiance data up into the middle atmosphere, which give it its high altitude sort of capability. And so a big jump in NAVGEM from NOGAPS alpha is now that it's a 4D VAR system, and it also uses ensembles to better calculate and constrain its error covariance, which is a big improvement over the sort of the NOGAPS idea. And so to give you a better idea of sort of how these measurements are in there and just some background on the NAVGEM system. So you can see here on the left, it gives you sort of the model grid spacing, where you can see ECMWF and NCEP and the NRL that's basically NAVGEM is the point of that. And then the black curve here is the operational NAVGEM that's run at NRL. And so if I just move forward here, this gives you some sort of altitude extent to the observations that are assimilated into the model to give it its high altitude capability, and the altitude in which these things, the vertical extent of these things, and also the radiance data here in the upper atmospheric channel. And so the model grid spacing is around 110 kilometers. It uses sort of this hybrid sigma p coordinate where it's terrain following at lower altitudes, and then transitions into constant pressure surfaces with height. A key thing here is there are some things that are parameterized, non-orographic gravity wave drag, and sort of the photochemistry and ozone and H2O and these things like this. But the important part is it's recently been sort of independently validated. So what I'm showing here are, in the red is net, and I guess I should say this. It's an improvement over NOGAPS Alpha 2 because we have it has a 3-hourly cadence. And so even though the analyses are updated every 6 hours, the 3-hourly, the 4D VAR capability, they produce a 3-hour forecast, which has also been, is pretty good and has been validated. And so what you have here are independent meteor radar measurements at 4 different sites. The red showing the radar measurements that are hourly, and the black line showing the 3-hourly NAVGEM meridional winds. And so it seems to do pretty well. And this is up to about 88 kilometers. Now this is about, you're starting to get to the point where the data assimilation and the amount of data that the model is assimilating is starting to be much less. So it's not too much higher than this if the model is constrained by data. It's mainly model at this point. But one of the big things, especially for the upper atmosphere and this interannual variability, is this idea of this 3-hourly cadence and sort of this ensemble 4D VAR capability. When you look at, so this is a monthly mean plot of the semi-diurnal migrating tide and its meridional wind amplitude, monthly mean in January. And so this is what the old NOGAPS Alpha product looked like in its vertical extent. But now you can see with the NAVGEM, the 3-hourly eliminates the aliasing problem, but also gives you much better resolved scale sort of the semi-diurnal tides, which are important in the thermosphere and the ionosphere. Okay, so how we're going to nudge the model. And so historically, the Time-GCM has been nudged one way, and we're trying to propose doing it a little bit differently. And so it's what's called sort of analysis nudging, and it became popular in mesoscale weather prediction and WRF and things back in the early 1990s. And so sort of we want to do this idea of analysis nudging of the prognostic equations. And so it's been done before. It was done in the Siskin 2014 paper, but it was just done at one vertical altitude level in the TIE-GCM. Obviously, for the Time-GCM, we're talking about constraining the stratosphere and the mesosphere with NAVGEM. And so just to give you a general idea of how this nudging would work, what you have here is just a sort of an example of the horizontal momentum equation. And so you have your tendency term here and your change in time. This Fx here is supposed to represent sort of any of the dominant forcing mechanisms you would get on the right-hand side of the equation. So gravity wave drag, Coriolis, pressure gradient, these things. And so what we do here in analysis nudging is the difference between Time-GCM or TIE-GCM or whatever model we're using here from the NAVGEM is actually multiplied by this nudging term, which is weighted in altitude, which is weighted in time. So in order to not just turn the model on and shock it, you kind of ramp it up gradually. And also this nudging strength, which is going to be where I spend a lot of my time in the coming months. And so this is sort of the vertical structure of how that looks in altitude. So what that looks like is this. So it's basically saying down close to the model lower boundary, we're using all NAVGEM. Right, the NAVGEM nudging is turned on and it's strong. And then it falls off with altitude up until pressure level -7. So that's where the nudging is turned to 0. So this strength just gets progressively weaker as we move in altitude. We weight it in time, so I'm not showing this curve, but it's basically we ramp up the nudging. So it's not to shock the model, it's allow the model to kind of smoothly transition. You could think about it as spinning up the model. And then the last part is this nudging strength, or this time scale for nudging, which needs a lot of testing. But in this case, I'm using a time scale that's about 2 hours. And so the idea with this is now it becomes a tendency term when you add in this nudging strength. Because these differences here are just in meters per second, but now you add this and it's meters per second squared. And so it's an actual forcing term on the right-hand side of the equation. And so this is just one value that Siskin et al. Had used. I know Fabrizio in WACMX has used something like a 10-hour time scale, which is a factor of 5 less than this. And so just naively, what I know about it to this point is that sort of the stronger your nudging is, the more you're trying to constrain like shorter temporal variability, like waves, tides, things that have much smaller time scales. Whereas the longer you, or the bigger the smaller the nudging strength, the bigger the time scale. You're trying to You're trying to get the mean correct and things like that. So I guess here would be the best way of sort of this historical idea and how it's been done in Time-GCM before. You're just taking when you come in to calculate the momentum, for example, you just take a difference between the Time-GCM weighted in altitude from the observation that you have with the opposite of that weighting. And so then that determines your momentum or your U and V at that time step. And then you then step through and calculate all your tendency terms from that new sort of zonal mean wind or full wind. And the difference here is that in the analysis nudging, it actually gets added as a term on the right-hand side of this equation, and you allow the other terms to be unaffected. So meaning you're allowing the model to basically go through all its filtering routines and everything else by just adding an extra artificial momentum source. And so the point of this is you can really kind of quantify where you're nudging the model, where you're not nudging the model. And it can give you some idea into the physics, the underlying physics that the model was missing. And so at this point, we just started this, and so we have one test case, which is for the sudden stratospheric warming event in 2010, in January and February. So this is just one test case. And what you have here is the zonal and diurnal average zonal mean temperature at 80 north. It's a function of day of year starting in 2010 to just show you sort of the general features of the stratospheric warming. Now the major stratospheric warming didn't occur by the classical definition. Here's the zonal and diurnal mean U at 60 kilometers. Didn't occur until like around February 9th, somewhere in there. But you can see these strong westerly winds in the mesosphere. And obviously, since what we're concerned with is this idea of mesospheric composition, we're interested in this time period as well, even though by classical definition it's not a major sudden stratospheric warming until later in the year or in February. And so it also, I guess I also should point out, this was a geomagnetically quiet time for the most part. I believe right around the end of January, the 21st to the 25th, KP spiked a little bit to about 4, so medium, but it was pretty low solar activity, pretty low geomagnetic activity. And so what we did was we performed a couple of different simulations of the Time-GCM. We allowed the F107 to vary and KP to vary daily. We used a double resolution, and then the 3 runs that we performed was we just put NAVGEM in at the lower boundary, so just specifying the waves and tides and letting the model go. Then we did this zonal mean nudging, which Astrid has done here, where you nudge just the zonal mean temperature and winds, level -7. And then we have sort of this full analysis nudging. And so it should tell us something about what the model is doing in terms of not picking up stratospheric warmings versus picking them up. And so we're really using this sort of run as a proof of concept. Hey, we can do this, it works, the model doesn't blow up, and we'll go on from there. So what you see here is zonal and diurnal mean T at 80 degrees north. In the upper left is NAVGEM. This is if you just put NAVGEM in at the lower boundary. You can see it doesn't really do that well. NAVGEM, the zonal mean nudging, so following sort of Astrid's work, and then also the full analysis nudging. And so you notice it does a pretty good job. Down where the model is actually constrained and we're nudging it pretty strongly. There are differences as we start to get towards the top. And you can see that here, and this is in the early part of the year in both of these. And so the differences between those aren't necessarily clear, but I can say NAVGEM, we're not necessarily 100% confident that NAVGEM is giving us the right answer at those altitudes either. So what's right and what's wrong is still left to be validated. But the interesting part, and what we're interested in, especially for these interannual variations and the sort of the composition piece that I talked about, is now this is the zonal and diurnal mean U at 60 north. And so you can see here's NAVGEM. We cut it off above pressure level -7. This is the lower boundary. We know it doesn't do that well. But this is the zonal, this is if you nudge the zonal mean, and this is if you do the analysis nudging. And once again, down in the stratosphere and mesosphere, it does pretty well. But I think the interesting piece is now we've extended these up 2 more pressure levels. And the interesting part is the difference that you get above that. And so now we have to evaluate, okay, what's going on and relate this back to the composition. Are we doing the composition right? Is this doing a better job? Because there were some issues with the zonal mean nudging and sort of the altitude in which you stop nudging. In that case, you were getting these strong vertical gradients in the U winds that may or may not have been physical. And so just to kind of hammer home this point of the analysis nudging and the nice part about it. So now you can actually print out the individual nudging terms in the temperature U and V equations. And so like this shows at 2 days, which were represented by those vertical lines in the last 2 plots, temperature nudging, the U nudging term, and the V nudging term. And so we look at these as a function of altitude and latitude. And you can see where the model is saying have to put in momentum for some unaccounted physics, or putting in energy for some amount of physics. And so that has some very powerful implications in terms of what the model is picking up and what it's not picking up. And so sort of in summary, it's just that a lot, as we've seen prior studies suggest that eddy diffusion formulations sort of need to be considered now that we're better resolving and constraining our GCMs. The Time-GCM can self-consistently reproduce this SAO, and to our knowledge, it was at that time the only model that we knew that could do it. It doesn't seem to be driven by KZZ variations. It seems to be more of this internally forced oscillation that happens down in the middle atmosphere and then is propagated upward through molecular diffusion. Sort of the combined effects of this advective transport, tidal transport, and diffusive transport and atomic oxygen appear to be what's driving this. But specifically the individual mechanism, and this is what's doing it, is still unclear and still something I'm working on. The artificial terms in the Time-GCM don't drive the SAO. The system seems to produce it by itself. It doesn't really do a good job with the annual oscillation, the solar cycle variability, and at least to first order, we can nudge the Time-GCM with our NAVGEM stuff. It doesn't blow up, but there's a lot more to be done there in terms of that. And that's all I have. Thanks. Say it again, how much? I would say that I'm probably not the person to answer that, but I would say just a lot. It would matter a lot. Yeah, especially at the higher altitudes, because that is the one, I was talking with John McCormick before I left, and he was saying above like 90 or 95, like where they start to enter the sponge layer of the model and everything, that's the only measurement that they have. Because they're not assimilating any wind data or anything like that.
We did some experiments with WACO. If you just assimilate the lower atmosphere data, for instance, you assimilate stable and NRL, and especially during sudden stratosphere forming, you get quite significant improvement in the mesosphere. We added the upper atmosphere data.
Yes, Dan?
When you were nudging the zonal mean, were you nudging all fields to the zonal mean, or were you nudging the model zonal mean to the zonal mean?
Nudging the
global gamma waves.
Yes, and so it's nudging the model zonal mean to the to the observed zonal mean.
But you think those differences are about that time actually significant?
I think they are, because at least just from talking with Astrid and the stuff that she's published, it did have an effect with damping the tides and everything. And actually in Ashford's paper, they went higher because of that, because of some of these issues. And so I do think this analysis nudging scheme and the way that it's implemented allows for a little bit more forgivability, at least in the model, in terms of what it can handle, how hard you can hit it without it sort of, breaking down and starting to create transients. And so I do have to test some of that, though. It's one of the first things I want to look at is sort of the tidal damping in these different ways, but in incorporating that with the nudging strength. How hard can we really hit the model and have it work, and have it still work and give us something physical? Yes?
So what about the annual term? Any thoughts there?
See, it's hard for me to say.
Some people just say, well, it's sun Earth distance.
And we,
Off to that.
but
And certainly there is a component.
yeah, the sun-Earth distance is definitely, it's a component in that.
It's fine.
Part of me thinks it has something to do, like the SAO and the AO are connected, and it's because it's not a pure semi-annual or annual oscillation that the two are connected. In the Time-GCM, it's hard to say anything about the AO because the density is no good. And so, if you're off by that much in mass density and composition throughout the vertical domain of the model,
Well, but you can make that same argument about the semi-annual term.
yeah, but at least relatively it matches up. Relatively, the annual term doesn't match up. In the annual term, you'd be looking for more of a peak, just one peak and one valley. So I do think I'll say this. I think that the annual term and the semi-annual term, the mechanism that causes those two things are pretty closely related, and that the sun-Earth distance effect comes in to be additive to whatever that is in the annual term, at least in my mind.
But it's harder to invoke purely thermospheric or ionospheric mechanism for that.
Yeah.
Unless there's an amplification factor in the sun Earth distance that is somehow missing, which seems difficult because anything that, it's just an irradiance difference. Right?
Yeah.
So it would manifest in terms of solar cycle
Absolutely.
and everything else. And the other possibility that people talk about is, well, you have magnetic field morphology, which of course does affect the ionosphere annual term. But if you just look at thermosphere density and composition, it's just hard to imagine how to create that very dramatic July minimum without invoking lower atmospheric processes. And we do know that there are systematic differences in troposphere between the hemispheres, driven by topology, which manifest themselves through the troposphere into the middle atmosphere. So I've always felt that there must be something there, but we've never been able to mechanistically close on that.
And I agree with you, and it's wildly interesting to me that for 50 years this thing's been observed, but for some reason we can't model it.
People are only recently coming to the conclusion that the thermosphere and ionosphere components of this thing are in fact
Similar.
related or causal. And yet that's somewhat accepted now. But go back 20 years, it was not. And in fact, it was largely unknown. I would have claimed a similar evolution with regard to the mesospheric SAO and the thermospheric SAO, and yet you seem to be showing that they may not cause anything. Hard to say.
Yes, sir.
So, developing a multi-dimensional cheating function that we call nudging. So it sounds a little more sophisticated. Is apparently necessary because you don't follow the physics at the resolution necessary in all altitudes, latitudes, longitudes, say. The effective physics involved, it doesn't seem to be Coriolis forces, tidal waves, gravity waves, things like that. Do you have a feeling how much better the resolution has to get in a whole atmosphere model, including the thermosphere, to get these effects right, to get rid of the nudging?
That might be a question more for the Wacom people. Yeah.
It's missing weather.
Mhm.
These models have no
Weather.
weather
Mhm.
per se.
Well,
And
even
even
it's
if
not
they,
the weather that you would kind of think
not
today.
that
Mhm.
Time-CDM doesn't have.
But it
No,
must
these
be
No.
more than weather if these annual and semi-annual, very regular variations don't come up. They are not done by weather.
So there are two different things. So when you're trying to reproduce an exact of a stratospheric form, which is a random weather event.
It's episodic.
Solar
Yeah.
That's different. That's what the nudging is for.
Mm.
He's not nudging the model with Time-CDM,
Oh,
the
I
FAO.
Okay.
Mm. Well, at least not right.
It's a little unfair.
At least not right now. Like,
By the same token, I mean, what I said earlier about the annual oscillation, I'm making a claim, in fact, that weather affects the
yes.
seasonal climate.
Mhm.
Some
Some the
different in one summer.
and,
That's not a proven hypothesis.
and this talk is kind of just jointed in that way. What I showed you at the end is like, okay, we can do this as sort of a proof of concept idea. I can put this in. One is we don't have a NAVGEM run for a year, so I can't nudge it with something I don't have. But the goal is to be able to nudge the model over a year, seeing what I know the Time-GCM doesn't do well, sort of in these episodic events and different sort of solar activity levels and things of that nature, to have a good handle of it. So that way when I nudge the model and try to replicate one of these, the annual oscillation, okay, well, we know what the model's deficient at. And so it must be related to something that the model is not doing well, that hopefully is captured by, forcing the model in the right direction. So quantifying those nudging terms tell us something physical. And that's kind of what the end part of that was, hey, we can do this for sort of these episodic events. If we can do it for these episodic events, we should be able to do it for something that varies climatologically.
There's another question behind Michael's comment, I think, which is how much resolution do you need to get rid of some of these parameters?
Randomizations, yeah, and that's,
Gravity wave scheme
Mhm.
plague us. And I think the answer to that is probably, a tenth of a degree,
Mhm.
10 kilometers, something like that.
Yeah.
But then, of course, if we want to get rid of effective randomizations in the troposphere,
Mm.
it's a bit
even smaller. I mean, mhm.
But that's why these crazy resolutions. That's why people are trying to run stuff with these crazy resolutions. I think that's the ultimate goal: is to get rid of effective randomizations, gravity randomizations, all that stuff.
And part of this nudging, some people in this room have even showed you do better with a linear damping because of the mismatches between these parameterizations between what you're nudging. So there's a lot there. It might not all just be resolution. It might be in some way, shape, or form. Maybe what we're doing when we nudge is actually doing a good enough job of parameterizing the model, and we can sort of linearly damp it with altitude.
Yeah, you just want to be sure that you're not missing physics.
Absolutely.
If there are no more questions, thanks, Mike, again.
Nice.